Thank you, Jeff. Can people hear me? All right. I was actually here about a year and a half ago talking about the same topic. The difference is that then it was all this big future forward-looking thing where we were designing type systems and designing the software to check them and imagining how that would work out. And tonight, we have a similar talk, but we actually have over a year of experience of using this stuff for really, really real code at Dropbox. In fact, so real that all our code is still in Python 2.7. So, speakers, Jukka Lehtosalo is not here, but he's the founder of the Mypy project. He sort of, in some sense, made this all start. He wrote most of the code that we're still modifying and improving, and he designed definitely almost all of it. Greg Price and David Fisher are here and are going to do very important bits of the talk. I'll just start with a little reminiscing because I like to sort of think about all my amazing accomplishments. I did actually start thinking about this topic around the year 2000. I dug up an old talk where I said, let's add optional static typing to Python, and here's what it might look like. And it still sort of looks familiar, and many of the ideas are sort of better now, but recognizable. So in 2013 or so, actually 2012, 2013, Jukka started working on this for real. And since then, there's been a tremendous interaction between Jukka's ideas for Mypy, the Python community culminating in PEP 4a4, and work at Dropbox actually adopting this work. And some other early adopters like a chat system called Zulip that is open source. Greg is actually going to tell us why we want to use this, or tell you, I already know. Then I'm going to give a very brief summary, I hope, of what it will look like. Then David will show us what it really looks like when you're actually using it. David's a really good live coder. You are. Then there's some more stuff, just a tiny bit of an idea of how a type checker of this nature actually works. And Greg will bring up some actual data about how it has worked out for Dropbox. And then hopefully there will be plenty of time for Q&A. So Greg, if I may invite you.
All right. Hello, everyone. Thank you, Guido. Is this audible? Is this clear on the, excellent. So to see about why we're so interested in this, I'll start with a little parable. So, story that I've lived many times. Let's say you're editing some function that you've never seen before, or a function you wrote 6 months ago and you forgot all about it, and you're trying to figure out what's going on so you can add something to this or debug an issue, something like that. And any of you who work in a large code base, lots of people in it, you've probably done this many times. So this code, it iterates through some entries, and for each entry, it takes entry.data, and then it calls a method called validate on it. Great, OK, so it's basically all about what does this method validate do? OK, well, we can go search the code base for a method called validate. And if we're lucky, this might work. We might just find the answer and we're done. If we're less lucky, there might be 154 methods with that name, which is the actual number last I looked in the Dropbox code base. And this isn't a fluke. This is an artifact. These are not all subclasses of some common thing with a method. It's a good name, and popular names are popular. And in a smaller code base, and for a less excellent name, maybe you'll have 15 results, or maybe you'll have 3 or even 2, and you still have the same problem. Which one is it? OK, well, so which one is it? That comes down to what type, what is an enter.data? What type does it have? Right? So to understand this code, it comes down to what type does this expression have? And this is very, very common in my experience of trying to understand what some piece of code does. So, well, if you knew what entry is, it'd be pretty straightforward to figure out what enter.data is. And if you knew what entries is, it'd be pretty straightforward. So great. So what's entries? Well, we could go and try to guess it from the context of the code around it, see how it seems to be treating it, what it seems to expect this type is likely to be. That's a pretty common way to end up doing this in my experience. It's not very satisfying because you could guess wrong. You could be more systematic, go for call sites of like whatever function this might be part of. And that could work, but now we have all these call sites and we have actually the same problem recursively. Right? At each of those, we're now in the business of trying to work out what type the argument has that we're passing for this parameter, if it's a parameter for the function, something like that. If we're lucky, then it's easy there. It's a constant, a literal, something like that. It's easy to figure what type it is. If we're less lucky, we really have the same level of problem again. And so we end up in this whole search tree going through callers, through thousands of lines of code, potentially, reading just to understand what this one line here, what this like little snippet of code is doing. And this is something that I've done many more times than I would like to do. And I want to never do it again. And more broadly, this problem of understanding what the code is saying is a big deal. It's what we spend a lot of our time doing when we're working in any kind of established code base. To put a number on it, a little over a year ago at Dropbox, we had a survey on several subjects. And one thing we learned was that about 40% of the time engineers spend doing software engineering, they're spending understanding code that's already written. So we want to make this better. How do you do that? Well, one thing that you could do that you hear recommended when you describe this problem is we could rewrite everything in some other language that has static types. There are some problems with this. So for a start, we have over 4 million lines of Python. So this would be a lot of work to rewrite all of those in some other language. And moreover, it's not just a lot of work, but it's really disruptive. It's hard to get any other work done at the same time. There's a well-known story of this you can look up by Joel Sposky about Netscape. But in general, it's a famous thing that can kill companies. But the biggest reason I don't think I really need to say much about to this audience, we don't want to use some other language. We like Python. We use the languages for some things where we need to, but for most code we write at Dropbox, I don't think there's any other language we would actually be happier working in. So that strategy won't work. OK, what else could we do? We could have some kind of special doc strings or comments, or we could use one of the many conventions for how to write that. And that could be OK at first, but people don't always update them. You've probably seen this happen, especially when it's not even, when you make a change and it's somewhere like far away in a different file that becomes now no longer true because of the change you made. So this happens all the time whenever you have a lot of comments and doc strings you want to rely on. And then at some point you get burned spending hours chasing a phantom because the comment lied to you. And you realize you can't rely on these. And they lose their value pretty fast when you can't rely on them. So that won't work. What else could we do? We could try to do some kind of whole code base type inference. This is a strategy that people do pursue that has great success in some other languages that aren't Python, that have important differences in Python. There's some problems with this. For a start, it doesn't actually directly address the main thing that I want to do, which is understand the code when I'm looking at it. Right? If you have some fancy program that does this inference across the entire code base that chases like all the flow of data and works out what type anything must be from understanding the entire swath of the code, that doesn't directly help you when you're looking at this piece of code. Maybe if you insist that everybody who's working this code base use your favorite fancy IDE that you've integrated with this fancy thing, then maybe that can solve it. Or there's other ways you could work around it, but you still need another thing. More fundamentally, it's just really hard. Python is a really pretty dynamic language. It's not easy to actually trace through everything that's going on in the whole code base and get to the last bits, especially as you need it to be fast. you have a multi-million line code base. You want to be able to like make some change in one piece of it and get the answer as to whether you broke something or get things right. And particularly if there's by design, the consequence of this strategy is that in order to understand anything, you need to understand everything. And so the most dynamic core, which of course you have somewhere in your Python code base probably, because why else are you using Python if you're not using the dynamic stuff somewhere? The most dynamic core limits how much you can understand any of the program that depends on that. And in some cases, it could even be fundamentally impossible and depend on something outside the source code itself, even though the interface is perfectly fine and well-typed. So that strategy won't work either. OK. So what can we do? Well, type inference is a pretty neat idea. Let's do that, but let's do it locally. Let's not try to understand the entire code base all at once through the sheer power of the intelligence of the program we write that analyzes it. That goes a long way to make it tractable, to make it something you can actually do, and to make it efficient on a multi-million code base. And it gives you the opportunity to draw that typed boundary around your highly dynamic core libraries so that on all the much more straightforwardly typed rest of the code, you can just reason from that and not have to try to somehow tackle the very dynamic core. And it also solves the problem of making it accessible if you write annotations in the source code, then no matter how low-tech or how diverse the way that you're working on the code, you see it right there. The type's right there. And those annotations, unlike a mere comment or docstring that doesn't have some kind of type checker, you can actually rely on it because it's being verified by this type inference. And that means also standardize some kind of notation in Python for writing down the types of things, so you can have this. If you do all this, you're now writing down types in the source code that describe like the expectations about what types things should be at runtime, and you're checking them statically. You might call it static types for Python, and that is what we call it. So we added static types to Python. And there's still some constraints you need to deal with. There's some challenges. It's essential that you make it possible to introduce gradually on a code base, that the typed part coexists with the untyped part, because you have millions of lines of code and you don't want to go back to the rewrite problem. And it's not trivial. There's a lot of work to do to make this work, but we can do that. So that's our strategy. And just a word on why this is happening now. As Guido said, people wanted this in Python. Guido's wanted this in Python for a long time. It's obviously valuable. The answer is happening. The reason it's happening now is just that nobody knew how so many years ago. Nobody knew how in 2001. The thing that makes it challenging, we like dynamic types, just in small doses in those core libraries where you're doing it to implement some really nice interface that you couldn't otherwise easily do. That's part of what makes Python great. If we wanted truly everything static, we could use Java or something. So we want to keep some dynamic types in a code base that now is primarily statically typed. One name this goes under is gradual typing. Nobody knew how to do this in an effective way for a language like Python until 5-10 years ago. The very first really working idea of something like this came out of academia around 2006. Jeremy Seek was one of the investigators on that. And so that's how this happened. So Mypy started with Jukka's thesis. He's a co-author that's absent. He works in the UK, which he finished in 2013, came to Dropbox. Work since then, sort of open source and on the side, and we started really supporting full-time work at the beginning of this year. And Mypy is a type checker. It is a standardized type notation, PEP 484. That was last year. And lots of teams now have adopted it at Dropbox. Not because we've somehow forced them we couldn't if we wanted to, because they really like it. It makes the code much better, makes them much more productive. And so with that, I'll hand it to Guido for some more words on what this looks like.
Thanks, Greg. Mic on again? Yeah. So I feel this is like the tip of the iceberg. We're looking at a function of 4 lines here. It works. We call it the greatest common denominator of 10 and 15 is 5. Now let's add some type annotations, and this is what the type annotations using PEP 484 look like. You add column int for arguments and arrow int for return types. Okay, well this function only deals in integers, that's why it's all int. So this program is still valid Python. Since the beginning of Python 3, this optional argument annotation syntax has been supported. So it still works, still prints 5. But the next thing we can now do is we can type check this program. Let's run Mypy on this program. Well, it's almost underwhelming because there are no bugs in it, so Mypy produces no output. By the way, in Python 2 you can also do this. Python 2 does not have the nice annotation syntax, so you can hide that signature in a comment. It's not the same as the kind of comments that Greg rejected previously, because these comments are checked by the type checker. So to run this with Python 2, of course you say Python 2. To run it with Mypy, Mypy in --py2 mode will check this code and validate that it's valid Python 2. Actually, this particular version works just as well in Python 3, so you could run it without that flag too. But let's make it a little more interesting. Let's introduce a bug. Calling the greatest common denominator of a string and a number is not a good idea. Let's see what happens when you run that program. That's a really confusing traceback. On the other hand, if you check that same program with Mypy, you'll get a very clear error message. It actually points out the line where the problem occurs, which is the call to GCD, not somewhere in the middle of running it. And it tells you what the problem is with the types there. So this is the kind of progress we're talking about. There's lots more to this. It doesn't just work with built-in types like int and stir. You can import types from other modules, either your own or standard library. You can define your own classes. Classes can be used as types in annotations. When something doesn't return anything, you just say arrow none. And that means that the checker understands that it doesn't return anything. So call sides will know that there's nothing there. One last feature of the type system that's kind of important and useful is you can also say, well, this returns a list of strings. This is a really simple function that takes a single string and just creates a list with that thing repeated n times. Now, actually, this function works for other things too. You can pass it an arbitrary object or an integer or another list, and it will just repeat that. We can express that in the type system, and this is as far as I'm going today. You introduce a type variable, and then you say it's a function from type t to list of t. And we use square brackets in Python because we like our square brackets. In Java, it's the same story with angular brackets. Okay, I want to come back a little bit to the gradual typing stuff that Greg already mentioned. We really want to roll this out gradually on a large code base, because we really need to be able to say, well, we have 500 files and we want to type check all of them, but we haven't annotated all of them. So we have some annotated files and some unannotated files, or maybe one file that has some classes or methods that are annotated and some that aren't. And we need to have something useful happen in that kind of case. This is a little bit tricky, and I don't want to sort of go into too much detail, but basically we've come up with some simple rules. Annotations are always optional. You never have to annotate everything. When a function is not annotated, it's also not type checked. And that goes both ways. The body of the function is not type checked, but the calls to an unannotated function are also not type checked. Don't think too hard about that. This is the research that started in 2006. How do we really do things like this for dynamic languages? Here's a very simple example. I think David has a similar one that will make it more clear. This is a really tiny legacy code base. Imagine these are two functions very far apart in different files, different packages. And there's actually a bug. And I'm guessing that the bug is that the call site is wrong. But I'm not really sure. It could be that the function once worked for strings just as well as for numbers, and someone changed it. If you type check this, it's kind of disappointing because it just says, I can't find any problems with this because nothing's annotated. So let's add an annotation to the function that's being called. Well, unfortunately, because the call site itself is not annotated yet, it's still not finding anything. If you approach this from the other direction, say you have a large code base and you're sort of annotating some code in one team that calls code that's not annotated yet because it's owned by a different team or it's just in a different package and you haven't gotten there yet, same thing happens. Mypy doesn't see the errors yet. You might think, well, that's kind of disappointing, but believe me, if you have a large code base, if Mypy started complaining about every single call that it thought might be wrong, you'd be completely overwhelmed in the noise. It's like turning on a new lint rule over 4 million lines of code. However, once you've annotated both sides, Mypy will actually tell you, something's wrong here. Now we still have to figure out which one was wrong. Well, it's pretty clear in this case that the function was really meant to work on integers, so the call side is wrong, and we can now go fix it. I'm not going to explain much about that. So how do you do this? How do you deal with a large legacy code base? What are sort of concrete steps you want to introduce in your project, your company, to introduce Mypy successfully? Well, here's a rough set of steps that we did successfully at Dropbox. We're still on the last step. Zulip pretty much ran through all these steps in a few months. Their code base is not quite 4 million lines of code. So the first step is set up continuous integration that runs Mypy on every commit. Or if you think that's too much, you can do it every hour or whatever, every minute. This, on an unannotated code base, will still give you a certain amount of background noise for top-level code, because top-level code is always checked. I didn't mention that previously, but that's a fact. So you have to do a certain amount of upfront work, not too much, because there's usually not that much top-level code, and it's usually not all that broken, hopefully. So you fix the errors, and now you have your first clean Mypy run. The next thing you do is sort of lock in that success by running Mypy before you allow a commit through. And at Dropbox, we have something called a commit queue that does a whole bunch of shenanigans and runs unit tests as well. If you've got a smaller project, maybe you can do this with a git pre-commit hook, while the previous thing you could do with post-commit hook. All sorts of interesting solutions, but basically, you now require that Mypy is always clean. Next step is that you introduce a change in your process where you say, well, all new code should be annotated. And again, if you have a small project or a mid-sized project, you probably already do code review. Your reviewers can sort of point this out to the people who are submitting code. In a large project, you might be able to write a little linter that checks for new code that has function definitions without annotations. Anyway, at some point, you get to the point where you're going to have to make a big effort to try and annotate everything, but you don't have to get that done all at once. And in fact, that is very often a sort of an ongoing, continuous process. And we're very much still in the early stages of that at Dropbox. Finally, well, I guess there's profit to be made. So one more technical topic, and this is sort of the vanguard of Mypy's capabilities. Suppose you have a function that didn't expect to be called with none. So if you actually combine that call with that function definition, it will break. You get a kind of mysterious Python error. It's not unique to Python. If you can figure out which languages these are, you get a prize at the end. So what do we do about this in Python? Well, let's add an annotation, see what happens. We run it with Mypy. Dang it, Mypy did not catch the bug. Why is that? Mypy's current default mode of operation is actually closer to the way it happens in C++ or Java than in some newer languages, or than maybe you would want. And in fact, PEP 484 prescribes that this ought to be caught. Mypy just hasn't caught up yet. But there's a new flag, same program. Let's run it again. Let's check it again with a new flag, strict optional. Now Mypy will actually find that there's a problem, and it'll tell you, well, you can't call it with none if it's not declared to take a none. What exactly is something that could be none? Well, it's a union of some concrete type and none, and we can express that as a shorthand using the keyword optional. So now we run this, and dang it, it's still not bug-free because we just added more annotations. We didn't actually fix the bug in the program. It's just now sort of, we've told Mypy that call is okay. You should be able to call this with none, but now there's a bug in the implementation. What you have to do is somehow you have to introduce a none check in that function. And if you write it like this, Mypy actually understands enough about checks for none. It can also check other things like isInstance. And it knows that this gets a clean bill of health because we've actually fixed the bug. And just to sort of point out that this is a cool thing that all the cool kids are nowadays doing, a similar feature is appearing in other languages that have been designed in the last 5 or 10 years. And with that, I'll let David switch to demo mode. I'll let you do the...
Thanks, Guido. Just going to do some unmirroring magic here, hopefully, so you can all see what's going on, or rather mirroring magic. Excellent. All right, these are probably a little big. Let me narrow them down a little bit. Let me check this for line length. Yeah, that should be reasonable. Hopefully everyone can see this somewhat decently. I'm going to give a brief live demo of Mypy so you can get an idea of what using Mypy in practice might actually be like. And also to review a little bit some of the things that Guido said to give you more of a feel for them. So briefly, oh dear, I'm spoiling everything. Briefly, here's the kind of toy module that I have. It's for a bank account. We have an account class, which just has a name and a balance. The balance is going to be a float, which is not something you'd want to do for a real bank. You probably want an integer number of cents, but this is a questionable bank, so that's all right. So you also have a bank class. The bank has a name, and then it has a dictionary from account holder names to accounts themselves. And we have an open account function that takes in some initial balance. You get a sign-up bonus, and it creates an account for them. You can get an account by name, and you can also deposit some particular amount into a named account. And then finally, we have this kind of module-level donate function at the bottom, which is going to take the bank, some list of names, and an amount you want to donate to each of them, and it's going to return how much you actually donated overall. So hopefully that's the pretty understandable basic structure. So let's start by running Mypy on this. And what do we see? No output. That means that Mypy is happy with the program, and it doesn't see any problems. And again, this is, yet again, a consequence of gradual typing, which we've found to be very useful in a large code base, but we think is really important for introducing it into even moderately sized code bases, because otherwise you're just swamped with errors in the beginning, and you can't make progress. So great. So let's add a basic annotation here. Let's start with this open account function. So the self type we don't need to annotate. Mypy understands that has to be the type of the class. But name is going to be a string. initial balance is going to be a float. As I said, it's kind of sketchy. And if you look, you can see that this function doesn't return anything. So as Guido said, we can talk about that by saying arrow none. So let's run Mypy on this once again. And we can see that, oh, look, in member open account on line 25, which is here, this line, unsupported operand types are plus, float, and string. That means you're adding a float to a string, and Python's going to give you a runtime type error if you try to do that. And if we take a quick peek at this program, we can see that, oh, look, we quoted our sign-up bonus. We probably don't want to do that. So if we fix that, we can run Mypy on this again, and we'll say, hey, great, looks good. Excellent. So let's continue on with our annotating here. Let's annotate getAccount. So we can see usage of a user-defined class. So this takes as an argument a name, which is a string, and it returns an account type. And that's very easy to spell. You just use the class name, pretty much the same as all built-in classes. And if you run Mypy, you can see it doesn't complain. Now, this might be a cause for slight consternation, because as you can see on the following line, we're trying to look up the account by the length of the name that's passed in, which is pretty silly. But at this point, Mypy doesn't know anything about what goes into this account's member variable. And that's because the init method of this class is not annotated. And so, all right, let's go fix that. So name is a string. Init methods return none because that method itself doesn't actually return anything, even though the constructor does. And now we can see if we can make some progress. Well, whoa, we get a bunch of errors. What's going on? Well, they all center around this line, line 13, where it says, hey, you need to add a type annotation for this because I don't know what you mean. We can see that this is a dict, but that's not enough to know what the key type is or what the value type is. Mypy will be able to infer this if you have an assignment to it, like if you append something to the dict in the next few lines, but here nothing happens nearby in the program. And so it doesn't try to guess wrong. Frustratingly, it just says, hey, please give me some more information here. So the way we do that is with an inline type comment, which is like #type:, and then you can give the type. And this is something that you can do for all initial assignments. And in this case, it's a dictionary from string to account. And you write that with a capital D dict because it lets you use this square bracket syntax. We do some dunder get item magic on the meta class. If what I said just sounds completely nonsense, it's fine. So we have to import this capital D dict from typing. This is important even if you just have it in a comment, so Mypy knows what you mean when you say capital D dict. But you'll also see these in non-comment places, and then it's important for runtime as well. So now let's see what happens if we run Mypy again. And great, OK, now we get an error on line 29, which is back here, this line. It says, hey, you're trying to index this with an int, but you really need a string. And that's great. This is the error that we wanted to get all along. And so we can fix that up and check it again. And boom, clean bill of health. So we've made good progress annotating this so far. So let's keep on going. In fact, let's jump all the way down to this donate method. So it takes a bank, which is just, again, another user-defined class like before. It takes a names. And names, if you look at this function, doesn't have to be a list. All we're doing is iterating through it. And so we'd really like someone to be able to pass in any sort of iterable. And we can indeed specify that. And conveniently, it is called iterable. Surprise, surprise. And we'd also like to be able to specify a value type, which you can do again with this square bracket syntax. And in this case, it's an iterable of strings. And there's also some amount each that we want to donate to, which is a float, because we're a sketchy bank. And as you can see at the bottom, this returns the total amount donated, so that's another float. And as I mentioned before, because this is some capital I iterable, we need to import it from typing. So I'll do that. So let's run Mypy on this. No complaints. Again, we can see something slightly sketchy in this function, which is that we're calling bank.deposit with an amount and then a name. But if you look at the deposit function itself, a few lines up, it takes a name and then an amount. And again, this is because this function isn't annotated, so Mypy doesn't really know anything about it. It's not going to try to look into it and guess wrong and do this long, expensive whole code base inference that will ultimately not be useful. It'll just say, hey, I'm going to be permissive until you get around to annotating it. And again, this may seem a little silly in this toy example where it's 5 lines away, but in a really large code base where this may be in some completely other team's function, this is really, really instrumental. And again, even in a moderately sized code base, it's nice to be able to introduce stuff gradually. So let's annotate deposit, takes a string and a float, and returns a float. And now, let's see if Mypy will give us our error. And indeed it will. It says, oh, look, the first argument to this function on this line is a, what is it? It's a float, but I need a string. And the second one is a string, and I need a float. So let's swap those two. And now, let's try again. And Mypy is happy. So now, I want to talk about something that Guido mentioned towards the end, which is strict optional stuff, which is something that I think is really cool and I'm really excited about. This has been in development for a while, and now we think is at a place where it's actually quite useful for people. So if you're starting to annotate something afresh with Mypy, we actually really recommend that you try this flag. So the way we can check this code with strict optional checking is just by adding the strict optional flag. And if we do, we see, hey, on line 35, which is here, we're returning none. But if you look at the type annotation, you claim to just return float, and none is not a float. So something is wrong. As Guido mentioned earlier, we can say that something can return either none or something else by saying optional of that thing. So in this case, we'd say optional float. Here, let me fix the line wrapping a little bit. So we can say this returns an optional float, which means exactly what's going on here. It returns either none or a float. And again, that's something that we have to import from typing. And now if we run Mypy again, we can see that it gives us an error in donate. It gives us an error on donate on this line. And why is that? Well, on the previous line, we're calling bank.deposit. And then we're trying to take that result and add it to some running total that we have. But you can't add a none and a float. It'll give you a runtime type error. And so that's why Mypy says, hey, you're trying to add a float and an optional of a float. The optional may be none, so this is not valid. So what do we do about that? Well, we should make the program actually correct. So we can say, if amount deposited is not none, then we'll add it. And otherwise, we just won't do anything, because no deposit was made, so we don't need to update the total. And if we run Mypy again, boom, it understands. So Mypy is actually pretty smart here with this strict optional flag. It can understand, as you see here, if you explicitly check that something isn't none, it's not going to be none for the remainder of that if statement. But it is a bit more clever. It knows if it's truthy, it can't be none. It knows if you check if it is none and then return immediately, it can't be none for the rest of the function and stuff like that. And so it tries to be pretty out of your way, and I think succeeds pretty well. But strict optional basically prevents the vast majority of non-type errors at type check time, which is really, really great. So that's all for this demo right now. If you're curious, have more questions, please play around with Mypy or ask us in the Q&A after this. And now I'm going to tell you a little bit about how Mypy works internally. Yes, if I can do this unmirroring magic. Excellent. Cool. So I'm just going to give a pretty high-level overview of how Mypy works. I want to show you that nothing too magical is going on, and that it's not that we went and hid in some crazy ivory tower for a long time and came up with a magical algorithm. It's a matter of a lot of hard work mainly. So Mypy has three main stages. The first stage is parsing, which you may or may not be familiar with. Sorry, I'll get to all of them in a second. So there's parsing, there's static analysis, and there's type checking. So to start with, I'll talk about parsing. I'm just going to give a pretty high-level overview of how that works here. The basic idea is you take some program text, and you turn it into something that the computer can understand. And that looks like a parse tree, which I drew out by hand here. Apologies for my very messy handwriting. Don't worry, we're not going to use it in the future slides. But this is important so Mypy can understand the structure of the code. And if you want to know more about parsing, there's a lot of good resources online. But it's actually a pretty deep topic. So the next thing that Mypy does is semantic analysis. And again, I'm going to go back and just use the program text here. But imagine that it's kind of iterating over this tree-like structure that contains the program, and it only has a sort of, if you want Mypy to understand something, you have to be very specific about it, right? It's a program, so it has a sort of myopic view, and you have to look through individual things pretty carefully. So the first thing that we have to do before we can type check stuff is actually understand what names refer to what constructs in the code. And we do this by, again, walking through it in a sort of meticulous way. So we start, say, with this variable x here. And we go and look at the various different scopes that it's in to see where the name comes from. So in this case, we look at this function scope. And we can see, hey, x is an argument here. So great, this is what this x refers to. And we kind of store that reference. And now we look at this O. And we look at this function scope. And there's no O here, so we have to look further. We look into global scope, and we see this O here. So now we know, OK, great, this is what this O refers to, and we store that. And kind of the same thing here with S. We look in the function scope. It's defined there by an assignment, so we match that up. And note that we find it in the nearest scope, so we don't confusingly get the global things. And the reason it works like this is just this is how Python works at runtime. And so we match the same semantics. There's a few more things here, though. There's this hex function right here, which is clearly not in the function scope. And it's not in this global scope. So where is it? Well, there's this module called built-ins, which has all of Python's built-in functions. And we have sort of a typed version of that Mypy can understand. And so we say, oh, OK, great. It's in built-ins. We can link that up there. And note that we don't try to look up upper yet, because we can't actually figure out what upper refers to. Because the only way we know what upper is actually referring to is by knowing what the type of hex of S is. And we don't know that yet at this stage. We only know, we can only figure out references for like names and not attribute references. So in all, this is about what the semantic analysis step does. It builds all these links. So now we can get to the type checking stage, which is the exciting part where we can actually tell you have errors. The type checking stage is mainly about going through the code, again, meticulously, layer by layer, and figuring out what the type of everything is. So let's start right up here at the top with 5. 5 is super easy, because it's an integer literal. So it has type int. So we write that down. And now we say, OK, great. Here's an assignment. On the left side is O. On the right-hand side is this integer literal. But it doesn't really matter. At that point, we just say, oh, look, on the right-hand side, we know it has type int. And so that means on the left-hand side, we know it has type int. And we can do the same thing for x and s here. So now let's get to the function. This one is easy. It's an annotated argument. And so we know it has type int. It's declared to. And now we start to get to some more exciting things. We can say, all right, what's the type of x here? Well, from the semantic analysis stage, we know what x refers to. X refers to this x in the function signature. And we already know the type of that x. It's int. And so we can say, great, this usage of x right here has type int. And the same thing with O. We know it refers to this O here. That has type int. And so this O has type int. And now we can do some type checking. We say, all right, let's look at x plus O. Well, we know that we can look up the definition of the plus function, and we can see that, oh, yes, if you give it an int and an int, it returns int, and that's valid. And so we look it up. We see that that's valid. And we know that now the left-hand side also has type int. And that's the same thing basically happens with the rest of the code. And that's sort of at a very high level how Mypy works. There's a lot of detail that was elided here. Actually, some of the type checking occurs in the semantic analysis stage and various things like that. But I hope this has given you some idea of how a type checker like this can work and how it's not too much magic and rather just like being very meticulous about all the various cases and and having the type checker itself go very meticulously through the code. And so with that, I want to hand it back to Greg to talk about what type checking, how type checking has gone at Dropbox.
All right. So I think most of what I have to say is this slide here. So we, as I said, started full-time work on this at Dropbox really at the beginning of this year. And at that point, there were 0 lines of statically typed Python in Dropbox's code base. And It's gone up rapidly. These dots are from the first month, so actually as of today, it's over 400,000 lines, which is a significant fraction of our code base. This comes from a lot of different teams at Dropbox deciding they want this for themselves. And in particular, our desktop client team, which is obviously very central to what Dropbox is, if you're familiar with the product, and is a major chunk of the Python at Dropbox. All the tech leads working in that code base got together and said, we have to use this everywhere. And they mandated that all newly written code there, and even any newly modified code, must be annotated with static types. And so that's driven a good part of this growth, and there's a lot more elsewhere. And in particular, people are adopting this because they have reactions like this when they use it. I won't read out all the words here, but this makes a big difference to people's experience of Python. It makes people much happier with their ability to read the code and understand what it's saying, and feel much better about working in this dynamically typed language that they otherwise would really like to be working in, and not worried that it's becoming difficult for them to understand a large code base as a result. Cool. So I hope you'll try this out. You need Python 3 to run Mypy, but you can perfectly well run on code that's Python 2.7 as well as Python 3. Nearly all our code at Dropbox is Python 2.7, and we're using it there. From PyPI, just pip install mypy-lang. It's not just Mypy for unfortunate historical PyPI reasons, mypy-lang, and then run it on your code. And with that, it's time for questions. Cool. Want to all stand up here? I can't hearing this up, actually. Yeah, however you want to manage questions.
Is this on? Yeah.
Cool.
I was just going to ask, in the Mypy example where, an unannotated program has no output and a correctly annotated program has no output, I assume there's an option to sort of give you statistics of, you might want to know
Yes.
how much work has been done over time.
Yes, absolutely.
And you might even want to parse that out, those numbers to kind of keep track of it elsewhere.
So there's sort of several possible answers to the question. So one, there absolutely is an option for exactly that, and it's where these numbers come from, for saying how much of the code is annotated. There's also a flag to say, actually treat the whole thing as if it's either as if it's annotated with sort of nothing annotation, but let's say at least type check the interior, or better yet, insist that everything be annotated, which that's a little much to insist on a large code base, but you can insist on it selectively in some files, or in a small code base, you might be suitable to do the whole thing.
Yeah, so if you have...
I would also like to point out that there is there are a bunch of report options, one of which produces HTML that is basically code listings with every line marked in red, green, or yellow, depending on whether it's annotated, unannotated, or partially annotated.
Cool. Yeah, and there's a version that's machine editable coverage compatible with things that do that.
Oh, yeah.
Cool. Next question, I think. Are we working from the mic there? Yeah.
You showed an example where you had a dictionary where you said variable equal to braces, and then that got annotated with a common type, right? How would you recommend to do it if it's a nested dictionary with the depth of it is much more with various different data types?
Yeah, so this is a problem that can occur whenever you're trying to talk about the type of something that has quite a complex type.
Yes.
One of the things that we do to make that potentially easier to read is we allow you to define type aliases. So you can say, like some subdictionary. If I had an account map type, which is a map of string to account, I could say account map equals dict of string comma account. And then if I wanted to have a dictionary of account maps, I could write int, a dictionary of int comma account map, and that's easier to read than dictionary of int comma dictionary of string comma account. But you could write it either way.
One other power of Python that I used most was variable arguments. So for that, what recommendations or what best practices you use?
So you can annotate variable argument things. I think right now we insist that if you do so and you want strong type checking, that all of the arguments be of the same type. If that's the case, then it is fully supported. If that's not the case, if that's not the case, then in writing it down, you'd be basically spelling out a full argument list anyway, right? Like if you wanted to, if you had like 5 different things and they each had varying types, then, well, maybe you're better off just putting them as keyword arguments, as non-mandatory keyword arguments, and giving them types that way.
One more question. In Java, we have these methods which says this throws exceptions. That is not related exactly to type annotation, but that make it much more cleaner code where we say these methods throw exceptions and have try except kind of thing. So will that also be introduced anytime in Python?
I'm not looking forward to introducing that. I actually have a feeling that even in Java, it's mostly seen as a failed experiment because it's incredibly difficult to sort of get it right, and most of the time people will sort of be forced by the compiler to put in, by the Java compiler to put in sort of nonsense code where they just say catch everything and then raise something else. It's not like, it encourages more code that is still wrong. So it's not very effective. And yeah, you can argue about that, but the long and short of it is that we're not doing that in Mypy or in PEP 484.
Okay, last question for Dropbox as such.
Let's make sure other people can ask questions. Feel free to go back in the queue and
Sure.
ask after.
This was just a Dropbox question.
No,
You can answer later.
Please.
Please let other people. Yeah.
I'm trying to figure out in your initial case, you see, okay, this validate, what does it do?
Yeah.
So I still don't see how it helps us reading code.
Uh-huh. Sure. Maybe I'll just quickly pull back on the screen. So the point is you're looking at some code, and it's you probably have a whole screen full of more code than this, right? And you're trying to understand what the code does. And maybe you come to lines like this, like what does this code do? Well, what it does is invoke this method called validate. And so to understand what the point of this line is, or understand like what the effect of it is going to be, you have to go and locate the implementation of that validate, or at least its documentation if you have documentation.
Okay.
But you need to identify the right validate method. And in order to know what that is, it depends completely on what the type is of the object it's being invoked on.
So does Mypy help figure out what the .data type is, and then you can like, this
I
is of that
see.
type,
Yes,
and
yes.
this
So
is
there's
the
sort of 2
validate.
levels of answer to that. Great, now I understand. Thank you. This is a good question. So I didn't draw this explicitly. So there's 2 levels of answer to that. One is the super low tech one. If say entries is a parameter to this function I'm looking at or something like that, I just have to I'm looking at the code with no other tools. I just have to look up to the top of the function, see, oh, okay, great. Entries is of type list of thing. And then if I'm reading this code, I probably already have worked out how it gets pulled out of there and so on. And so it's a thing. And maybe I have to also go look up what is the data attribute on that thing, or maybe I already know. Either way, there I am. The slightly higher tech way is if you're using really any kind of IDE. If you're using, for example, PyCharm, which already supports the PEP 484 annotations, the same type language that we use. PyCharm has long had a feature of doing its best to tell you if you mouse over something like that, tell you what the method is. But it's constrained by the fundamental limits that apply to trying to do whole code-based type inference. Once you start adding these annotations, it takes full advantage of those. And so if you just add that annotation, then you can very well expect that it will be able to tell you. You just mouse over the validate, and it'll tell you. And finally, you can do the same in for Emacs, VI, whatever else.
Yeah, so we actually have a prototype-ish, prototype but pretty well-working Mypy plugin for Emacs and Vim that will let you highlight some expression and say, hey, tell me what type of this is, and then it does. So.
Cool, thank you.
Cool.
Hello, 2 questions, that all right?
Sure.
Sure. So first question is, if you guys mentioned that metaprogramming doesn't work necessarily very well of this. What is the nature of the failure if there's metaprogrammers in your code? Does it for example, if there's like a literal inference that you could make, but there also is a metaprogram thing that messes it up, does it just give you the literal answer without telling you about it silently? Or would it just like say, don't know?
That's a really good question. Okay, so let me answer it in two parts. So one is if you have like a part of your code base that has a lot of metaprogramming and dynamic stuff, you can let it be dynamic internally and either like not type it or type it in this like very permissive way that we haven't really talked about here with the any type. And then have a like strongly typed boundary around that. So for the rest of your code base, you understand how to interact with it. For metaprogramming in general, it's depending on how understandable it's ultimately going to be. Like there's some metaprogramming that's just not really going to be intelligible at like type check time. If you read in some config file, right, we're not going to be able to understand that. Right now, I think we understand some metaprogramming. We understand some descriptors, like you can annotate the descriptor, and we'll understand that. I think there's more work to be done there, and that's something that we'll continue to do. We always leave some escape hatch, so if you can't really express it in the type system, there's always a way to say, hey, Mypy, just like, be quiet about this, I got it. And you don't get the type checking benefits, but you allow that like little piece of dynamicism to work even in the midst of a well-typed.
So would using super as like a cooperative class mechanism work, for example, in Mypy?
Super works.
Okay.
Super totally works.
Okay. Yeah. And then other question is, what language inspiration was used for Mypy, like Scala, ML, what?
Jukka's not here he's the only one who can sort of answer that. I think Jukka was very strongly inspired by Python, but also by, no, seriously, he originally designed a language that was inspired by Python, but not literally the same or even a subset of Python. It was a different language that had sort of was easily transliterated or transpiled to Python. So I don't know what other languages he was inspired by, but I don't think he was trying to emulate the sort of vanguard of type systems. He was trying to get a language that sort of struck a balance between Python's dynamicism and a sort of powerful enough type system so that you can do generics.
I see.
Because that's sort of, you really need the generics.
Thank you.
Thank you.
Does it make sense to have something like const that's like in C++, where you have an object that's not modified?
That's a good question.
It might be a good idea. There's no sort of easy way to wedge in new syntax. One of Mypy's amazing constraints at the moment is that it must be valid Python 3 syntax without Mypy. We're not adding any new syntax to support Mypy. The sort of the notation for generic types using square brackets, the function annotations, all syntactically was already in the language. So exactly how you would add a notion of constness, you'd probably have to spell it as this sort of similar to the way we spell it with optional. Optional square bracket and then some other type. You could say this is const square bracket and some other type, and then maybe you have one chance to assign to it and that's it. But we haven't really sort of explored that idea or sort of gotten any requests either. We have a very large tracker with over 500 issues, and I don't think that there has been a request for const.
I feel like we discussed it recently. Though. I don't know. Yeah, I think this is, as you can see, it's still a matter of some debate. It's something we're considering. If it happens, it would probably be pretty far down the line, and it would probably be something that is like Python specific and doesn't necessarily emulate. Like C has pretty confusing const semantics, right? So we don't want to emulate that.
Okay,
Thank you.
So I had a question. You talked briefly about doing the annotations for Python 2 versus Python 3 with a comment in the bottom. Is there a way to do that so that way it works with both,
Oh,
Absolutely.
it does.
Yeah, the comments work with both.
the comments work with both. So if you just do it that way as opposed to using the fancy Python 3 way with the colons and everything,
Yes.
you're guaranteed to work in both.
Absolutely.
Wonderful. Thank you.
Yes, and working with straddling code is like we make sure that Mypy that you can type annotate straddling code and have it work and type check in Python 2 and Python 3.
Because I don't like writing it twice.
That's right. Yeah. You'll want to then, like in your CI, both test it as Python 2 and Python 3.
Yeah.
That's all you want to do. Yep.
How much type checking will Mypy give me on the standard library?
Stubs. We have stubs for most of the standard library.
Is it-
You should explain what that.
Sorry, a stub file is, I think David had one little example where he said, oh, we look hex up in the built-ins, and the built-ins is like type annotations for the standard library. But stubs are purely there for type annotations. There's actually, syntactically, it's a Python file, but you replace the body of every function with just 3 dots.
So I could do the same thing if I also wanted type annotations on my favorite pip installed modules.
Yes.
Yeah,
And
okay.
you can even contribute those stubs to a separate repo called typeshed, which is shared between Mypy, PyCharm, and a Google type checking project called PyType.
Yeah, and we actually have stubs for a lot of popular libraries already, so you may be pleasantly surprised and find that they're there. Although not all of them are complete, and so if you get a message that says, "Hey, this function doesn't exist," and you're like, "No, what are you talking about? It totally does." It means the stub isn't complete, and we would very happily accept a pull request that adds it.
I was wondering if you'd care to speculate as to whether this can help interpreters generate faster code and stuff like that.
Oh, yeah, that's like, everybody hopes that if you add annotations to your code, it can also automatically be compiled to faster machine code. That's not actually our goal. There are other systems that do that. One of the best systems for accelerating Python code doesn't need any annotations. It's called Mypy. And it just does it at runtime by seeing what actually happens at runtime. There's something called Cython that actually has its own annotation-like syntax that compiles to C code. There would be some synergy by sort of letting something like Cython also work with PEP 484 style annotations. But in the end, the kind of type system that you need to describe things like, well, this is a dictionary from strings to lists of integers. The power and the strength and weaknesses of the type systems are different here than what you would need to generate optimal machine code, because for the machine code generation, you probably want to say, well, this is a 32-bit int and that's a 64-bit int and things like that. So the goals are not quite as aligned as you might believe they are from sort of buying into the philosophy of a language like C++.
I've noted that if you do annotations and then do a run call and just call it with Python 3, it'll still throw an exception. So it seems like part of Mypy at least is already in CPython. So just wanted to ask, what's this relation here? Like, what's logic is in Mypy as a separate package and what's already in CPython? Do you understand the question?
Yes, I think there may be a bit of confusion actually, because I don't think we said this explicitly, but type annotations don't have a runtime effect for the most part. If you say this function takes a string and at runtime you pass it an int, it'll happily take the int at runtime. It's only when you call Mypy on it that you'll get this error message. If the function doesn't actually work on an int and would crash at runtime, then you'll get the same crash as you would before. So basically the answer is all of this type checking code is in this separate Mypy package. The only thing that's in Python itself is this syntax, but that's been there for a long time.
This example is actually illustrating that, because if you run it, you get an error on a different place than when you check it with Mypy. One more, yeah.
So I have a question that's kind of, you never mentioned unit tests here. So I think so far we were putting more emphasis on unit testing dynamically typed languages. Is this something that you can use to help transition from Python 2 to Python 3? Since now you can annotate Python 2 code and maybe catch those differences and like automatically generate missing code in 3. And don't you think that if you add this, it's actually, let's say, giving you more rope to hang yourself, because you will say, I'm covered with type checking instead of I'm fully covered with unit testing, knowing that people might be lazy writing tests.
Yeah. So I think there's sort of two questions. One is about Python 2 to Python 3, and one about unit tests. The unit test is a good thing to address. So I see this as a different purpose from unit tests. Unit tests, in my experience, have never really solved this problem of like, how do we look at the code, understand it? So the best you could, unit tests, you could like go and try to find the relevant unit test and try to like infer from that like what it's trying to say about the code. I've never found an efficient way to try and understand the code. It's not nearly as concise or as local or as reliable as like the statement right there. This is precisely what should be happening here. So the primary purpose of this, of like understanding the code, is complementary to what unit tests do. I think there are a few unit tests you'll sometimes write that maybe are obviated by this. If the unit test is really strictly limited to this question of like, does it take the right types, or et cetera. But really, most of the unit tests that I see aren't substituted for, I don't think, by writing down types. And certainly in Dropbox, we still write plenty of unit tests for the same code we were writing down types for.
And like people write unit tests in Java, right? So the whole XUnit, like JUnit is the origin of XUnit, right? And it's all, so I think that covers perhaps that side of it. For Python 2 to 3, the answer is yes, it is very helpful empirically. So in principle, it should be, because if you think about what is the hardest part of moving from Python 2 to Python 3, I think in most people's experience, it centers on the hardest single part on the question of like string versus Unicode, right? Which is essentially a question of like, what type is this thing you're looking at, and is it supposed to be ultimately a byte string or a Unicode or whatever? And the problem of like propagating that through a whole code base as you figure out, oh, actually this part, we've been getting away with it being a string, but it really should be Unicode, or like vice versa, et cetera. Propagating it through correctly so you don't have like transitions. And I'm seeing nodding from the Facebook folks who are doing this practice, so I think this is probably true. Sorry? Sure. And then the sort of concrete empirical evidence is, we mentioned a couple times Zulip, which is an open source project that's a chat system that has adopted Mypy completely. And they did it actually in order to move to Python 3, in order to expedite doing that. They had a Google Summer of Code student this past summer with a project to move it to Python 3, and before that to add types. And if you go and track down the blog post, which was from, I think, October, I just search for Zulip Mypy, you'll find it. It goes into great detail about their experience, both like sort of with Mypy and other respects, and specifically how it helped them with the Python 3 migration, and it made that a much smoother and easier experience than you would otherwise expect for a code base their size.
Does Mypy support duck typing? Meaning, I don't care what type it's an instance of, I just care that it has these methods and these attributes.
Mm-hmm. So this is, the answer is right now, no. But this is something, well, okay, no, the answer is right now, sort of. If you're happy explicitly inheriting from an abstract base class, then yes. So if you can like say that you're an iterable, or you can say that you are a I don't know,
iterable sequence, like mapping. So in fact, for the bulk of the duck types that I generally hear people talk about in Python, which are all sort of a standard set of things that appear in kind of the standard library and built in and so on, like the ones you just named. All of those, actually, those specific duck types appear, they're provided for you in the typing module and you can simply use them directly, iterable sequence threads.
But not a user-defined.
Well, and for that, you can actually you can use the same mechanism that those do, which is we've reused and given like static meaning to the abstract base class mechanism, which has been in the standard library for some time now, the ABCs. And so you simply write down an ABC, an abstract base class that describes your duck type, and then you can go and use that.
But as for there's I guess the other half, which is like proper structural typing or like full structural typing. I think we've
which
largely
is sort of an academic term for duck typing.
Yeah, sorry, which is which is like duck typing made static, I guess. I think we largely think that that's probably a good idea, although we're still thinking about it, and so it may happen eventually. Is that a good characterization?
Yeah,
yeah.
That's
it takes some work.
A project.
Properly.
Yeah, yes, it would also be a big project
But
to implement.
it's on the radar.
So I was wondering if there are any tools that you know of, or if there's been any attempts to create something that would do some type inference and then suggest annotations to just make it easier to start.
Yeah, it's a thing that we're quite interested in doing. In particular, having seen how Facebook added types to PHP and called the result hack. And one of the elements that was quite useful for them was something just like you described, was a tool that they went and did whole program type inference and accepted that it wasn't going to be complete and it was going to be very slow and it was going to have all kinds of limitations, but it could give you suggested like annotations, and all those limitations are fine for that context. And I think that could be quite valuable. That will probably be an element of if you go to this this number slide at the end, and
lots of slides.
Yeah, a lot of slides. We'll be there in a moment. Moment. You go to this number slide at the end.
Should have gone there right away.
That's fine. We're good. Here we go.
Yeah. Right. This is sort of the very beginning of a curve. The 100% point is 10 times further that way at like 4 million lines. And so you imagine like logistic curve that we're hoping to follow here. I think for the middle part of that logistic curve, some kind of tool like that, some way of automatically helping you add things is going to be quite valuable. To go and tackle the large bulk of legacy code that isn't particularly actively maintained, but you want to have types on so that you can better type check the other stuff that you are working on. And there's a couple of complementary ways you can do that. So one is as you said, a fancy inference thing statically to go and work out in cross all directions. Another is to dynamically look at what happens in your code as you run tests, or as you run your test suite, or as you run production on maybe a sample production machine, something like that. We're interested in all of those. As I said, Facebook demonstrated one of those. We have a prototype actually that none of us, but one of our users over in the desktop client code base at Dropbox, whipped up for the dynamic approach. It just goes and uses set trace to observe at every function call what types are being used, and go and run that on your. And that produces a good draft.
Is this open source? Is this attempt?
That attempt is
Not
a
yet.
super rough prototype, and we haven't even reused it within Dropbox. But certainly anything that's actually useful, we would definitely want to. Yeah.
Thank you.
I don't know.
I don't know about
ring a bell.
Microsoft. Google has something called PyType that might be what you're thinking of.
Huh. I think I missed that talk. Mm-hmm. Yeah, that sounds to me actually a lot like the Google PyType talk.
The
I think it's
Google
possible to
thing
think
has
of
the
that.
same limitation.
And they had a slide that's precisely like that, so that's why I think it might be. Yeah, that team is focused on attempting to do whole program type inference as the endpoint, as the final strategy, which was sort of what I described on one slide there. Why we don't think that that's ultimately a strategy that will work well for solving the problem. But certainly we would love, to the extent that we can use or reuse parts of that tool for what was suggested just there, we would love to do so.
Yeah. I mean, and obviously we'd be happy to be proven wrong.
Yeah, that too.
Say,
Yeah.
So you mentioned close to the beginning that that teams can mandate new check-ins and to modified code and new code to be type inferred. Does Mypy take a diff or anything like that it would be able to validate that for you in an automated way rather than requiring people to be disciplined?
Yeah, so there's a couple ways that can work. One of them is like if you have a particular section of the code base completely typed and you want to make sure no one else adds untyped code, you can, there's this
config file.
There's a config file, and you can give per file flags. In this case, this is disallow untyped functions, or disallow untyped defs maybe. And it means you can't make a new function without it being typed, or you'll get a Mypy error. For the more complicated case of you want to just make sure all new code introduced or modified is type checked, I wrote a kind of simple linter based on, so Mypy uses, Mypy has its own part, the AST module, that is able to understand type comments. And so it uses that, and it's actually pretty straightforward to write something from that checks that all functions in some range are typed. That's something that could potentially be open sourced if people are excited about it.
Okay, thanks.
Hi, I was wondering if Mypy supported like first order functions or like lambda functions and how that would work.
Yes. The answer is yes, and it's getting better. Right now, there's a callable type where you can say here give like you say like callable of like int comma string, and then well maybe I should here. Yeah, here I'll show you what it looks like because it's pretty easy to mirror. The basic idea is the type would look like callable of like int string, and it returns say like nothing, or maybe like another int. This is a function that takes 2 arguments and returns an int. Cool. In the near future,
annotation.
Yeah. So this would be an annotation. So I could have like def f returns some callable, and then I have to implement that. We're getting better support for named arguments and stuff like that. There's someone at Dropbox, Naomi, and I don't remember how to pronounce her last name properly.
Safer.
Naomi Safer, who is currently working on that, and I think has like a pretty good PR for it.
Cool. Another question is, I don't know why you would necessarily want this, but is it possible to say, this argument can be like of a type like int or boolean, but like not string or something like that?
Union.
Yes.
Yeah, we have a union type.
Okay.
Yeah. So if you want to say like this function, takes some x, which is like an int or a string, and then like unconditionally say returns a string. Right? You could write it like this.
Okay.
And so union means it's exactly one of these types specified here, and you can use any number of types. It could be int, string, bool, etc. And it'll.
In fact, optional, which you saw, is just an alias for essentially for that with none.
Oh, with none. Okay, cool. And last question: what font is that? What font are you using?
I believe this is. It's either Consolas or Inconsolata. One of them is like a. I think it's Inconsolata is the open source one.
Okay. Cool. I like it.
Cool. Thank you. Me too.
We do too.
Can you use the mock like everyone else?
Oh yeah.
He's so tall he doesn't need to use the mic.
But we did have someone waiting, so.
Okay, hi. The question is, like, right now we have really fancy syntaxes for, like, we've been shown for arguments in function and methods, but at the same time we have something like comments for, like, typing in comments in, like, for variables and attributes, which kind of, it's basically the same syntaxes like we have right now in comments. And the first part feels really kind of nice because it's part of the language, but at the same time, those comments is kind of not really. So will it be always this way?
So,
like
that's a good
bit inconsistent.
When Guido said earlier that the language hadn't been changed at all, aside from the type annotations we showed you, he actually was lying.
Up to Python 3.5, it was the truth.
But now there is, in fact, syntax in Python 3.6 for variable annotations, and so you can write like
App 5 to 6.
And so you can write like x, which is an int, equals 5. Or if you want, you can just say x is an, or say y is an int. Both of these are valid. This is equivalent to say like x equals 5 pound type colon int.
Yeah, that's cool. And about the last one, if, for example, I'm assigning like two variables at the same time, how the comment thing works?
This does work,
okay,
right?
Yeah, that works.
Yeah.
As I thought. Anyway, thank you.
Hi. Question. When you went through this process at Dropbox of adding the type annotations to your code base, did you find yourselves rewriting any of the existing code to be less dynamic? Or did you find, well, either we'll kind of rope that part of the code off, or, it's the type system is so powerful for the way we actually use it in practice that it's good enough?
Yeah, we did rewrite a few bits of code, and actually almost every time the team that owned the code that had to be rewritten was very happy that they were forced to rewrite that 5-year-old legacy code so that it was finally understandable.
Yeah, and to be clear, we aren't rewriting any of this. It's the teams that work on the code decide to adopt it and to do what they do. And yeah, we've heard them say, oh, great, we've been looking for an excuse for years to fix that.
So can I quote you guys as saying then, would you say that by adding the type annotations, the code became more Pythonic?
I would say so. Yeah, there was some pretty out there craziness that, I don't know, some people might consider Pythonic, but I'm not so keen on that. As Greg said, the dynamicism is good in small doses.
So I started asking a moment ago a question, and motivation for that is we were doing a Python client for RESTly, which is LinkedIn protocol, API protocol that's typed. So you get JSON, but you get types as well. And one of the challenges was self-referential structures. So I pointed my colleague who was dealing with that to the work that you've done actually on typing. Can you just show how that's done, basically, when you have, say, node in a tree and you normally wouldn't write that the parameter is node in regular Python, but now when you are writing types, you have to refer to a class that's not finished, which is invalid syntax. So how we do that?
So yeah, that's a good question. So let's say I want to have some class C, and I want C to have like a self.next. I don't know. How do I actually give this a type?
Well, in a type comment, you don't even have to.
Yeah. Okay. Let me use the other way then. Cool. So you put it in quotes. Is the short answer made long? The answer to the other part of like, can I write a recursive type? I don't know if that was part of your question or not.
But this is a recursive.
Yeah, you can write a self-referential class definition using the forward references. You cannot currently write a recursive type alias. That is the thing that, and I'm sure if there was enough demand, we would add that.
Like?
Yeah, you can't currently do that, even if you put it in quotes. But we could make that work.
Yeah. but the answer is like no, because it's hard, not because we think it's bad. Yeah.
How long does it take to run the Mypy analysis on the 400,000 lines of code that you have? And does it do some sort of caching in case you make a couple of lines of change and then you have to run that again?
I think the number that we usually use is it type checks about 3,000 lines per second. We don't have a single run that type checks all 400,000 lines of code. It's split half and half between two repos, each with about 200,000 lines, and I think it's 2.5 minutes each, pretty close. Yeah, we're keeping an eye on that. We also do have an incremental mode that caches intermediate results, and we're still sort of debugging corner cases of that.
But it also works pretty well, so if you think you might want to use it, give it a shot, and we'd love your bug reports. Is that fair?
And it really is much faster.
Yeah. And also we're looking at speeding up the overall runtime because it's a little bit slower than we'd like. But for anything that's not horrendously huge, it's pretty decently speedy. Cool. Well, thanks a lot for coming. Thanks a lot for all your questions. We should be around.
Thank you.
Thank you very much.
Jeff.
So, and thanks for answering all those questions. Yeah, it's probably a record for the most questions. Yeah. So does anyone have any announcements or anything at the end of the meeting? If you do, otherwise, have a nice evening. Thanks.